In the classes so far, we have talked about the convergence or divergence of various sequences, including the sequence of partial sums for a series. But what are sequences? Sequences are functions from the set of natural numbers to some set, but we were interested mainly in sequence of real numbers, so for us sequences were functions from n to r. But many of the sequences that we saw, like n, 1 by n, 1 by n square, or more generally say p of n by q of n, where p and q are polynomials in n, these were all restrictions of functions from r to r. Like, for example, x, 1 by x, 1 by x square, or p of x by q of x. For convenience, let me name these. So let me call this sequence to be an, which is f1 of n. Let me call this sequence bn, which is f2 of n. Notice generally I do not write a sequence in the function notation, but here I want to look at them as functions. So that is why I am explicitly writing the function notation as well. I am writing the usual notation for sequences like a and b and etc. And I am also writing it as some f1 of n, right? So that's what I am doing. So, and 1 by n square, I will call it cn, which is equal to f3 of n. And this will be dn, which is equal to f4 of n. Okay, and if those are the names for these sequences, then this would be f1 of x, this would be f2 of x, this would be f3 of x, and this would be f4 of x. Okay, so in some sense it's the same function, and the sequence is just a restriction of the function to natural numbers. And we've already seen the convergence or divergence of these sequences a and b and c and etc. More precisely, we know that f1 of n diverges. More precisely, it just gets bigger and bigger, so it goes to infinity. That's what the intuition says, right? On the other hand, limit n tends to infinity of f2 of n is equal to 0. Limit n tends to infinity of f3 of n is equal to 0. We cannot say much about the limit as n tends to infinity of f4 of n. Why? Because we don't know what p of n and q of n are. Once we have fixed p of n and q of n, we know how to calculate the limit if it exists. If it converges, then we know how to evaluate it. So it's because we know these, it's natural to ask the question, what happens to limit x tends to infinity of f of x? It's kind of natural, right? Because in fact, we should intuitively feel that limit x tends to infinity of 1 by x is equal to 0, right? Because x is getting bigger and bigger, and hence 1 by x has to get smaller and smaller, and hence it should tend to 0. Can we make sense of this is the question. To answer that question, let us revisit when we say that a sequence an converges to a limit L. This time, however, we will use the function notation rather than the notation an. We say a sequence f of n converges to L if for every epsilon greater than 0, there exists an n that depends on epsilon such that mod of f of n minus L is less than epsilon for all n greater than or equal to n of epsilon. Notice that in this definition, we are not really using anything specific about natural numbers. So the exact same definition could have been used for functions from real numbers to real numbers. More precisely, I could have said, we say a function f from R to R converges to L if for every epsilon greater than 0 there exists an n of epsilon such that mod of f of x minus L is less than epsilon for all x greater than or equal to n of epsilon. Okay. All I did was that instead of f of n, I wrote f of x. And instead of for all n, I made it for all x. That's the only difference. Apart from that, it's all the same. Correct? So we can define convergence of functions from real numbers to real numbers. Let us go through it once more and make sure we understand everything. What do we mean when we say that a sequence converges to L? We say that as n tends to infinity, as n approaches infinity or n becomes bigger and bigger, the value of the sequence becomes closer and closer to this value L. Similarly, for a function f from R to R, what we want to say is that as x tends to infinity, that is as x becomes larger and larger, the value of the function, this time it's not a sequence, it's a function, becomes closer and closer to L. As all we require is to make x large enough or make x bigger and bigger, there was no reason for us to use n of epsilon, which is a natural number. We could have used this to be where x is greater than some real number. Instead of saying that x will be greater than some natural numbers, we could have said that there exists some x of epsilon belonging to R, that means there exists some real number such that whenever x is greater than or equal to this real number x of epsilon, we have f of x mod of f of x minus L is less than epsilon. We could have said that as well. I first started with the other thing so that it is closer to what we have studied for sequences, and actually both of them are equivalent. Why are they equivalent? See, a natural number is a real number. So if there exists, so saying that there exists an n of epsilon is saying there exists an x of epsilon, right? So it's, on the other hand, whenever we have such a real number, there will also exist such a natural number. Why? That is Archimedean property. Whatever real number you take, you can find a natural number greater than that. And if something happens for all x greater than or equal to x of epsilon, it will also happen for all x greater than or equal to the natural number greater than x of epsilon, right? So we can always find, if there exists such an x of epsilon, you can find a natural number n of epsilon, such that the same thing happens. So the two are equivalent. So you can ignore if you did not understand this. This is like a remark, but if you understand, it's great. Finally, sometimes instead of saying that f converges to L as x tends to infinity, which is a long statement, we might just say that limit x tends to infinity f of x exists. Okay, which is often easier to write. So we might use this alternate formulation with the same meaning. Now that we have a formal definition for the limit of a function as x tends to infinity, let us try to prove that our intuitions are correct. For example, let us try to prove that limit x tends to infinity of 1 by x is equal to 0. To prove this, we want to show that for every epsilon greater than 0, there exists an n of epsilon such that mod of 1 by x minus 0 is less than epsilon. Okay, we already know from Archimedean property that there exists an n of epsilon such that 1 by n of epsilon is less than epsilon. We can find such a natural number from Archimedean property. So if you take x to be greater than n of epsilon, then this implies that 1 by x is less than 1 by n of epsilon, okay, which is less than epsilon. Hence, this inequality holds. So we have the fact that limit x tends to infinity 1 by x is indeed 0. Prove in a similar fashion that limit x tends to infinity of 1 by x square is equal to. This is just an homework. What about the more general class of examples, the rational functions, which is functions of the form p of x by q of x, where p and q are both polynomials. Of course, unless p and q are explicitly given, we cannot really talk about convergence or divergence. So we need it explicitly. So we will take one example. So let's say something of the form, let's say 4x square plus 5x plus 3 divided by 3x square plus 2x plus 17. Okay, let's take limit x tends to infinity of this. Can you evaluate this quantity? I hope you will at least be able to evaluate this if instead of the x's you had n's. That means you have a sequence 4n square plus 5n plus 3 divided by 3n square plus 2n plus 17. I hope that in that case you can find the limit. Please pause the video and try to solve it yourself before I give out the answer. Hope you paused the video and actually solved it yourself. Anyway, let me walk through the solution. So what we are interested is in 4n square plus 5n plus 3 by 3n squared plus 2n plus 17. We know that a by b is equal to a by c divided by b by c. So if we divide the numerator and denominator by the same quantity, nothing will change. So we divide the numerator and denominator of this fraction to get 4n squared by n squared plus 5n by n squared plus 3 by n squared whole divided by 3n squared by n squared plus 2n by n squared plus 17 by n squared, which can be rewritten as 4 plus 5 into 1 by n plus 3 into 1 by n squared whole divided by 3 plus 2 into 1 by n plus 17 into 1 by n squared. So now we can use the fact that limit of sum is equal to sum of limits, which will tell that the numerator converges to 4. Similarly, the denominator will converge to 3. And because we know that limit of quotients is equal to quotient of limits, we will get that the limit of this whole quantity, limit n tends to infinity of this is equal to limit n tends to infinity of this is equal to limit n tends to infinity of this, which is equal to 4 divided by 3 from whatever I told earlier. So what do you expect this limit would be? From our earlier experience, we know that we should expect that this limit is also equal to 4 by 3. How will we prove this fact? See, the thing is, for sequences, we used limit theorems for sequences, correct? But for functions, we have not proved it yet. We will prove later that we can do it, but we will see some other things before we do it, and you will understand why I am delaying the proof after some time. So, we do not have the limit theorems, and if we do not have limit theorems, how will we prove this is the question. The good news is that once we have the correct guess 4 by 3, we can use just the definition to conclude that this function indeed converges to 4 by 3 as x tends to infinity. Let us prove that now. So how will we prove that? What we are interested in is 4x squared plus 5x plus 3 divided by 3x squared plus 2x plus 17 minus 4 by 3, which is equal to 12x squared plus 15x plus 9 minus 12x squared minus 8x minus 68 whole divided by 9x squared plus 6x plus 51, which is equal to 7x minus 59 whole divided by 9x squared plus 6x plus 51, What has happened? 12x squared and 12x squared got cancelled. 15x minus 8x is 7x, and minus 68 plus 9 is minus 59. So that's what we did. And this quantity by triangle inequality is less than or equal to 7x by 9x squared plus 6x plus 51 plus 59 divided by 9x squared plus 6x plus 51. And as soon as x is positive, 9x squared plus 6x plus 51 is greater than or equal to 9x squared. So 7x divided by 9x squared plus 6x plus 51 is less than or equal to 7x divided by 9x squared. And similarly, 59 divided by 9x squared plus 6x plus 51 is less than or equal to 59 divided by 9x squared. So this thing is equal to 7 by 9 into 1 by x plus 59 by 9 into 1 by x squared. Okay? And we know that both of these can be made arbitrarily small, because 1 by x can be made arbitrarily small and 1 by x squared can be made arbitrarily small. So we can make this less than or equal to epsilon. So because of that, we get that 4 by 3 is the limit of this function as x tends to infinity. Before we go any further, I want to revisit sequences and kind of define when we can say that a sequence tends to infinity. Here we won't say it converges to, but it kind of diverges off to infinity. So, but we will still say that it tends to, it approaches. Okay. So we say a sequence xn tends to infinity if for every m in n there exists an n that depends on m such that xn is greater than m for all n greater than n of m. So I could have introduced this notion when I talked about sequences, its convergence, its limit, etc. But I did not introduce it at that point because it was not really necessary for us at that time, and somehow I realized that I need it to do what I want to do now. So that's why I introduced it. But anyway, now that we have defined this notion, let's try to understand it better by looking at some examples of sequences that diverge off to infinity. The first example would be the sequence an is equal to n itself. Clearly, that diverges off to infinity. Another example would be bn, which is equal to n squared. Okay, so n squared also tends to infinity. In general, we can say that if we have Cn is equal to some p of n, where p is a polynomial in n, then Cn will tend to infinity. Also, moreover, we can say this, but this is a little difficult to see, but I will still leave it as an exercise. We can say that dn, which is equal to p of n by q of n, where degree of q is less than degree of p. I leave it as an exercise to prove that all these sequences tend to or diverge to infinity. So why did we suddenly go back, revisit sequences and define the notion of a sequence diverging off to infinity? We did this to actually be able to look at the notion of a function's limit as x tends to infinity in a new light. Hopefully, revisiting the concept of the limit of a function as x tends to infinity in this new light will give us a better understanding of the concept. And we will do this by proving a theorem. The theorem states that a function f of x converges to L as x tends to infinity if and only if for every sequence xn that tends to infinity, f of xn, notice that f of xn is now a sequence because xn is a sequence, so f acting on xn is another sequence. This f of xn converges to L. Let us repeat. A function f of x converges to L as x tends to infinity if and only if for every sequence xn that tends to infinity, f of xn converges to L. Let us prove the theorem. So, proof. In order to understand the proof better, I will name the two statements. So, this statement, let's say, a function f of x converges to L as x tends to infinity. I will call this statement P. And the other statement, for every sequence xn that tends to infinity, f of xn converges to L. This statement I will call Q. So to prove this, what do I have to prove? I have to show that P implies Q and Q implies P. This is what I have to prove. Okay. So now let us do each of these cases one after the other. So first we will prove P implies Q. This is the easier side of the proof. How do we prove P implies Q? What do we have when we say that a function f of x converges to L as x tends to infinity? From this what we have is, for every epsilon there exists an n that depends on epsilon such that f of x mod of f of x minus L is less than epsilon for all x greater than n of epsilon. That's what we have from the definition. We have to use this and prove that if we take any sequence xn that tends to infinity, f of xn has to converge to L. So what do we have in our hand? We have a sequence xn that tend to infinity. What is the meaning of this? This means that for every m, there exists an n that depends on m such that xn is greater than m for all n greater than n of m. So far we have done nothing. We have just written down what we have. That's all we have done. Now what do we want? Okay, we want mod of f of xn minus L to be less than epsilon for all n greater than some n dash of epsilon. I am putting n dash only to note that this number can be different from the earlier n of epsilon. So for all numbers greater than n dash of epsilon, f of xn minus L, the modulus of that has to be less than epsilon. This is what we want. So how do we ensure that this happens? To ensure that this happens, we will take m is equal to n of epsilon. Why would that suffice? It will suffice because n is greater than n of m, where m is equal to n of epsilon, implies that xn is greater than m, which is equal to n of epsilon. Okay, this will imply that mod of f of xn minus L is less than epsilon, because that is what we had here. See, our xn is greater than n of epsilon, so f of xn minus mod of f of xn minus L has to be less than epsilon. Hence, this part of the proof is complete. P implies Q is completed. We will prove Q implies P using proof by contradiction. Okay, this is proved by proof by contradiction. So what do we have to do? We will assume Q and negation of P. So we will assume Q and negation P and arrive at a contradiction. So let us unravel negation P for this purpose. So negation P is negation of, for every epsilon greater than 0, there exists an n of epsilon such that mod of f of x minus L is less than epsilon for all x greater than n of epsilon. This is what we have to negate. So let us negate this. How do we negate this? There exists an epsilon greater than 0 such that for every n, mod of f of x minus L is greater than epsilon for some x greater than n. To make the dependence on n clear, I will call that particular x as xn. So what do we have now? We automatically have a sequence xn, right? Moreover, what is special about this sequence? The sequence has this property that mod of f of xn minus L is greater than epsilon for all n. What does that imply? That implies that f of xn does not converge to L as n tends to infinity. Now this would contradict Q if xn diverged to infinity. But the fact that xn diverges to infinity is clear from this statement because xn is greater than n. So because of that, we know that xn diverges to infinity. And because we have xn diverges to infinity, this statement, that the statement that f of xn does not converge to L as n tends to infinity, contradicts Q. Thus the assumption that Q does not imply P has to be wrong. So we have completed the proof that Q implies P. So what is so great about the theorem we just proved? The theorem tells us that we could have as well defined convergence of a function as x tends to infinity in the following way. It is, we say f of x converges to L as x tends to infinity if for every sequence xn that tends to infinity, f of xn converges to L. These two definitions are equivalent is what we proved in the theorem. Why is that important? It is important because this might be more intuitive for some people. Moreover, this helps us express convergence of functions in terms of convergence of sequence. So we could express something that we just learned in terms of something we already knew. And these kind of connections are always important in understanding things better. Finally, even though it is more difficult to prove that f of x converges to L using this definition than the earlier definition, it is often easier to show that f of x does not converge to L as x tends to infinity using this definition. Let us go through that once more. See, to show that f of x converges to L using this definition, what do I have to do? I have to look at all possible sequences that diverge to infinity, then evaluate f at on that sequence, that is, calculate f of xn, and see whether f of xn converges to L or not. This is like too much information to handle. On the other hand, to show that f of x does not converge to L, what do I have to do? I have to just find one sequence xn that tend to infinity, but f of xn does not converge to L. So that part is often easier.